Ball, the director of the Frontiers Science Institute, and I want to welcome all of our guests in the auditorium as well as our online event guests. This is the 53rd Annual Frontiers Science Institute, and today we are going to have 7 student presentations, and I know you're going to enjoy them as much as I will. So I'm going to call up Maurice Wood, who is going to introduce our first speaker.
Hi guys, you guys know me, Maurice Wood. These 2 students are 2 of my mentees. I had them start out 6 weeks ago on a project that was actually my project for my senior research. It involves optics. Namely the Schlieren method. And so I hope you guys enjoy their very good presentation. I've seen it before. Yeah, take it away.
Hello, I'm Jacob Oz, and this is Jessamyn Hutchins, and this is Imaging the Invisible. Okay, so here what we're loading up is a slow motion video of a Schlieren image we took. Here's a matchbox and a match that I'm about to light. And this is slow motion, about 300 frames per second. You see the frictional heat coming out, and there the match is actually igniting. So pretty cool. What you see that looks like you would think would be smoke, this is actually the heat coming off of the match and causing a distortion, allowing us to view it. Very shortly, I'll come in and blow out this match, and you'll see the turbulent flow coming off of that. Very shortly. There it is. Coming in and blowing out the match. Okay.
All right, so this is the Schlieren system. So Schlieren comes from the Greek word schlier, meaning streak. And what this allows you to do, this system allows you to see the changes in the refractive index of air. So when air is different, or there is another fluid substance in the air, you will actually be able to see the shadows cast by this. So it allows you to see the shadows cast by changes in the air. And these currents will become visible. This here is an image of Jacob exhaling. You can see the air coming out of his mouth. So in 1672, Robert Hooke was looking up at the stars, studying astronomy, and started thinking on what was making these stars twinkle, and he realized that it was actually the atmosphere that was causing the twinkle in the stars. So this is how he discovered the principle of the Schlieren. Later, he ended up with a man named August Toepler, who came in and started working with lenses and light sources to see if he couldn't recreate this effect in a smaller scale, allowing you to see air disturbances in a lab setting. Refraction is when light enters another medium and changes velocity. If you have a different temperature of air, hot or cold, or you have water, the light will enter this after being in a certain medium, such as the air around us, and it will actually change velocity. It will slow down and it will bend. So in this image, you can see that as the light appearing to be bent. Well, it is bent, and the pencil looks as it is bent in the cup of water. So this system takes advantage of refraction and allows us to see this bending of the light in a way. So you'll have a light going towards a concave mirror, and this will reflect the light back towards the wall. Normally, it would reflect it all to a nice, clean focal point, but when you add a disturbance into this test zone, you end up with some of the light being jogged off the side of it. So it goes outside of this focal point. We insert a razor at this spot, and it blocks off this light, which will create a shadow on the resulting image or the projection. The rest of the light is allowed to pass completely through, giving you a high contrast image of the distortion here, and that allows you to see the Schlieren image.
Okay, so that was a very simple setup where you have one razor blade, and so you can see one plane of view, basically. So with the dual-bladed setup, instead of having one razor blade, you now have 2 razor blades. You have one razor blade orientated vertically, another one horizontally. This now allows you to see 2 planes of view simultaneously. So as you can see here, the green shows shows up very strongly here, and that's the vertically orientated razor blade, and here's the horizontally orientated razor blade in red. So here's how the system's set up. You have your light shining onto the concave mirror and being reflected back to a focal point. Now, to extend this focal point a little longer, we have a lens so that we can fit all of these optics. Otherwise, you'd be trying to cram a bunch of optics because there's not enough room. So this extends the focal point. Then it comes to this beam splitter where the light is split into two pieces. So we'll follow this ray here. This ray goes past a horizontally orientated razor blade. So a razor blade like this is reflected off the mirror, put through a red color filter, and then hits another beam splitter, which will shine it into this lens and camera. So the other beam goes and is taken, the other part of this beam goes through a light filter. This takes out a little bit of the light, makes the image just a bit more dim, and that's because otherwise the green would overpower the red. Then it goes past its vertically orientated razor blade, reflects off the mirror through the green color filter to give it a green color, and then recombined with the red to form a nice yellow. Okay, so here is the actual lab setup in our lab. So the concave mirror is somewhere off here, and it reflects the beam into here, and here's the lens, extends the focal length. Here's your horizontally orientated razor blade, the vertically orientated razor blade. Here's the red color filter, green color filter. The two beams recombining to form this nice yellow beam that's being magnified, and there's the camera down here. This is the magnifying glass. And blade placement on this setup is very touchy. You saw how the razor blades were inserted. Now, if you have a razor blade that's a little before the focal point, when you're putting your blade in, you'll see a shadow coming on the same side you're putting your blade in. Now, if you're a little past the focal point, you're sliding your blade in, and the shadow will come from the other side. But if you get it just right, it should uniformly fade. However, when we were placing the blades on this dual-bladed system and in our simple clearance, we noticed a phenomenon known as spherical aberration. And this is what textbook spherical aberration looks like. It's when the light isn't all focused, there's a distortion in your mirror or one of your lenses, and that's what it looks like. And you can see it very clearly here with the red, and then the outside ring, and then the green right there, and also here in our test image.
All right. So one of our main projects was to locate the source of the spherical aberration. It either had to be the concave mirror or the first converging lens, because spherical aberration occurs when light is shown on the curved surface, and it should be focused all back to a singular point, but some of the light around the edges might end up being sent off in stray directions. This is how you get the spherical aberration pattern. What we had to do was bypass the initial system, so this was no longer in use. We used a beam splitter to do this. And we shot it straight past its first razor blade and into a camera to see if we couldn't tell whether the spherical aberration was coming from the mirror or not, because the light was coming directly from there. What we discovered was that the spherical aberration did remain and was most likely sourced from the mirror. A secondary test that we did, we inserted the lens back into the system just beyond the focal point, as it would have been in the original system, just to see if the lens had any effect on this at all. It went into the camera. We noticed that the spherical aberration still remains. As you can see in this image here, the spherical aberration is there, the dark and the light. And we discovered that the lens did nothing to help or hinder the spherical aberration and wasn't a problem within our system. Another cool thing that you can do with this, to show that all the razor blades are being used, is to use glass. When you put the glass straight up and down in front of the mirror, the light will go straight through and hit this razor blade where it should. So you'll get both red and green light coming through, the nice yellow in there, and that will be your image. Now, if you take the glass and you actually roll it away from the mirror, this is your mirror, and you have your glass, hold it like that, you're going to have the light ending up to be jogged upwards by the glass in refraction, and will actually hit this and block out one of the colors of light, giving you an oversaturation of the other. Now, if you go the opposite direction, bringing the glass towards the mirror, you will get the opposite effect. It will be dropped down, stuck underneath the blade, and give you an oversaturation of the other color. This also works if you tilt the glass from side to side, and so that shows that the vertical method is also being used.
Another way to demonstrate the dual-bladed system's capability of seeing two planes at once is with the laminar airflow. And so here we the air coming out, and it's got a bunch of vortexes in it. Laminar flows, they have a fluid, it's into parallel sheets that rub against each other without any friction. And that's a laminar flow, and it would appear it's like a straight line. But you can see this is very turbulent. Here is another slow motion video. Here's the head of a hair dryer that I'm about to turn on, and you'll see the turbulent flow that we're going to try and make laminar, because our air source was a hair dryer. And there you can see it coming out, you saw the boiling out, and then see how it's kind of wavy? That's turbulence, and we had to try and make that look like straight lines. So our first design was based off of what they used to make fountain water laminar. And so you have your filter at one end, then a bundle of straws in the middle, and then a nozzle that expels it all. Bundle of straws gets the water, in this case, flowing forward without any vortexes in it, recombines it, and expels it through the nozzle. But as you can see in our image right here, that's still a pretty turbulent flow coming out. So we thought the nozzle and the filter were being counterproductive. Took them off and took a test image with just the bundle of straws. And as you can see, we got some very nice straight lines coming out of our system. So we just trying out another design. We designed one with just parallel slats. And our first one was out of paper, but we had a little trouble with that because the paper would wiggle around and create turbulence in our image, as you can see right here. So we went to a little more robust materials of cardboard and cardstock. And when we used these, we actually did begin to get a nice laminar flow coming out. We think we could improve this laminar flow by increasing flow rate just a little bit, but the hair dryer did not have a higher setting, so we have not tested that hypothesis yet. So there are some incredible applications of this dual-bladed Schlieren. Right here we have a smartphone, and it's playing a song. You'll notice here this is the distortion occurring from the song being played out of the speaker. So it's a pretty cool effect.
All right, so we took a bunch of images with these systems just to show how it works. This first image is cold air being shot over a piece of paper. When this happens, you will end up with a difference in pressure, and the paper will actually be brought up towards it. So this paper was flopping over before we took the picture. This shows both the red and the green cleanse very well by showing the air canister with its straw and the screwdriver. So you'll see the red and the green. This also shows that, and it also shows cold air being shot directly towards a screwdriver head, and from there it sinks. Up here we have one of the images from our single-bladed system. It is a hand in a fairly high contrast system. You can see the heat rising off of it. And this is a similar image using the dual-bladed system. This is cold air sinking over a cardboard tube. This image here is high contrast, shows just a bright band of light. This is two images from our single-bladed system, a polarized lens on the dual-bladed system, and air being shot directly towards the mirror on the dual-bladed system as well. Okay, so I walked into this lab and I saw the mobile Schlieren, or not the mobile Schlieren, but this massive lab table, 12-foot lab table, a big mirror on one side, and a bunch of optics at the other side. And to take one of these images that you've seen, you would have to turn off the lights and put it in front of this mirror. Now, I thought it would be really cool to be able to walk outside and observe these air currents. So I thought, why don't we remove the mirror, replace it with a lens so that you can have viewing beyond your setup. So this was my initial idea for the design. I would have ambient light come in and be focused by a converging lens to the razor blade, where the razor blade would be inserted at the focal, and then it would be put through a magnifying lens and an eyepiece, and then the whole thing contained within a box so that you would not get light interference. However, when I set up a test setup, here's the test setup, very simple. You've got your razor blade, your lens, and then you project it onto the surface. And when I looked at the image, it wasn't, that this system provided, it wasn't as I had hoped. You can see there, you can barely see the flow coming out of my air duster. And so I thought of a way, how could I improve this image? And so here was my first idea. I thought maybe instead of having an ambient light source, I would collimate my light. And collimated light is just light that's focused to infinity or has all parallel rays. And how you do that is you have your light source at the focal point of a converging lens, and then it will collimate the light. So I tried putting this into my system. So here I have my light source at the focal point, a converging lens, my collimated light where I can view the disturbance, and then this going into my box system.
However, when I set this up, yet again, I faced the issue of the image was very blurry, and I couldn't see what I wanted to see. You notice you could see heat coming off people's hands on the other images with the dual-bladed system. On this one, you couldn't see it at all. And so I thought, that's not helping really at all. And so the next step that I thought was, the Schlieren uses light to view all these disturbances. And when you have a very small lens, you're only letting in a small amount of light. And so if you had a larger lens, you'd let in more light and possibly get a clearer image. So I did not get to test this. And we would just like to thank all these people for their support, their time, and their funding. Thank you very much. So any questions?
Yes.
So what does the razor blade do in your
All right. So when you have the light that's been sent aside, it's going to go in a different direction. The rest of the light's all going to go out in a perfect triangle. This other light's going to go sort of over here, kind of defying the triangle. You're going to cut off that light. So all those weird lights, they're going to get cut off. So instead of seeing those light rays going out there, you're going to see a shadow in your image. So the razor blade just provides you with the shadow. Yeah.
Okay, so the question was if you could use anything other than a razor blade, and there have been, like, using a pinhole. You know, you could also use a pinhole if they be sent out, and supposedly that would give you all planes of view because you'd be cutting off light on all planes. But you get a fuzzy image. There was a problem with using a pinhole. Any other questions? Ben?
So what's the advantage of using
All right. So the question is using two colors. What's the advantage of using two colors? There's not really much of an advantage, but the two colors are there to help demonstrate that both planes of view are actually being seen.
And it helps you differentiate which direction the flows are coming. Because when it's a solid yellow, you're seeing that both are present, both planes are present, and then when you see a saturation of either green or red, it means that's the plane that the airflow is moving in.
What are the advantages of achieving a laminar flow?
Okay, so the question was an advantage of achieving a laminar flow. When we have a laminar flow, it appears as just a straight line of that color going across the screen, and so it's a nicer image and demonstrates the system better. Whereas turbulence, you have swirling and you have bits of yellow and green and red all in it, and it's not a straight line.
So in other words, it means that we don't have to set the system to a very high contrast image. We can have more light coming through in the end. We don't have to put the blades in as far if we have laminar flow.
Do you believe that if you achieve a laminar flow, you have a application?
The question was if we achieved the laminar flow, would it have wind tunnel applications? And the answer is yes. Schlieren are already used for wind tunnel applications, but they don't have this dual blade setup. And so when they want to see a different plane of view, they have to run the whole test again and reset up their system. And so that's an advantage of this one. You set it up and you can go and take your test. Any other questions?